Let's see if we can go ahead and get started on the notes from Chapter 6. This has to do with separation of variables. So first of all, solving differential equations. Well, you need to know basically what it means to solve a differential equation. And what that means is that you are going to find the original function. Find the original function if you are given the derivative. Okay, now we all know we've done this before. You can find the original function from the derivative by integrating. But what I want you to think about is if you integrate and we normally have the plus c, that means you're finding the general solution. So in this case, if the derivative is 2x, then the way we're kind of thinking of it is if we integrate, right, if we integrate the 2x, then we're going to get x squared, and we would write plus c, right? So that's the general solution. But think about this. What about a differential equation that's in implicit form? In other words, what if instead of trying to integrate 2x, we're trying to integrate, say, 2xy? Well, we can't do that. We can't integrate if we have both x's and y's. So we're going to do something that we call separation of variables. So I'm going to first of all give you the steps, and then I'll kind of show you what I mean by each one of those steps as we go through an example. So the first thing that you want to do is separate the variables. Separate the variables. And you know what, I think what I'm going to do is I'll actually go through each step as we go along. So if I'm going to separate the variables, not only does that mean separate the x and y that's over here on the right side, but that means I need to separate the dy and the dx. And I know in the past we've thought of dy dx all as one term, but really it's okay to separate dy and dx. So the idea is if I'm going to separate the dy and dx, in order to get the dx part over on the other side, if you think of it as a fraction, right? If I want to get something out of the denominator, then I would multiply. So if I'm going to separate the dy and the dx, if this is my equal sign, the dy is going to stay on this side, but if I multiply by dx, then that means it's in the numerator on the other side. Okay, so I've separated the dy and the dx, and now let's look at the 2xy part. Well, the 2x is already over there on the right side. Oops, I wrote that wrong. There's dx, right? I separated the dy and the dx. So the 2x is over on the right-hand side. So let's leave the 2x on the right side because that's where I have my dx. But that means that I need to move the y to the other side. And think about it, since I'm multiplying by y, to get rid of y, I would have to divide. So actually I'm going to divide by y, and I'm going to look at it as a 1 over y on the other side. So basically what I've just done is separate the variables. Okay, so the second step is once you separate the variables, then you can integrate both sides. I'm going to integrate both sides. And it's okay to integrate now because I don't have the x's and y's mixed up. I can integrate the left side and it'll be all y's, and I'll integrate the right side and it'll be all x's. So here's what I'm going to have. On the left side, when I integrate 1 over y, I'm going to get natural log of y, absolute value, right, plus c. And then on the right side, when I integrate 2x, I'm going to get x squared plus c. Now I want you to look at something. Notice I have a plus c on both sides. Just because I used a c in both cases, that doesn't mean they're the same constant, right? Either side could have a constant added. So I think what we should do from now on is, instead of writing the plus c on both sides, if you think about it, if I were to, let's say, whatever this constant is, if I were to move it over here and combine it with the constant that's on the right, I would have a new constant. So really, I don't need to put it on both sides. Let's just get in the habit. We will always just put it over on the right side with the x terms. Okay, so I have just integrated both sides. And then the last step, step 3, is to solve for y. Solve for y. Because remember, solving a differential equation means you're finding the original function, or you're finding the original y. So in this case, if I solve for y, I'm just doing algebra. It's not really calculus right now. How can I get a y out of a natural log? Well, you can think of it as changing it to exponential form. I think last year in your pre-AP, pre-calculus, I think the way she said it was, well, let's look at it as, let's look at it as basically making both of those have a base of e, and I'm not sure what term she would have used to do that, but basically I'm going to have both sides to be a base of e, because then what happens, e to the natural log of y cancels and you just have y. And at this point, it's okay to just write y instead of absolute value of y. I only needed the absolute value because when it was in the logarithm, I needed to make sure it was positive. Now that it's not in the logarithm, I'm not as worried about that. And then on the other side, I have this e to the x squared, and then notice the plus c is up there in the exponent with the x squared. Now, so I've finished with step 3, but I do want to talk to you about some algebra and some notation. I want you to think about this plus c in the exponent. Well, if I have exponents that are being added, that means it came from multiplying the same base. So this is kind of the same as saying e to the x squared times e to the c, right? Because if I'm multiplying the e's, I would add my exponents. Well, let's go a step further. This e to the c, I mean, e is a constant, c is a constant, so e to the c is just a big old constant. So instead of writing it as an e to the c, I'm just going to think of it as a big old c in place of, now I'm not saying that these are the same c, right? But it's just a new constant, and then it's being multiplied by this e to the x squared. And that tends to be the notation you'll see. So y equals c e to the x squared. Now let's look at the directions. Notice it said find the particular solution, right? Particular solution. And what I had said up here above is general solution means you're going to have a plus c. But if I want a particular solution, that means there must be some information they've given me so that I can find the value of c. And since they've given me an ordered pair for the original function, I can find the value of c. So I'm going to put in a 2 in place of y and a 0 in place of x. So I'm going to have 2 equals c e to the 0. And since e to the 0 is 1, that means c equals 2. So the answer that they're looking for, the original function, y equals 2 instead of c, e to the x squared. So this is the particular solution that actually has 0, 2 on the curve. All right, so let's look at another example. Find the equation of the curve, so that means the equation for y, that satisfies this differential equation. Well, if I want to find the original, I'm going to separate my variables. So let's think of it this way. If I separate the variables, not only do I want the dx to move up to this side, but I want this y to move over to this side. Okay, so the way I'm going to do that is I'm going to start by moving the dx over to the right side. That's separating my dy and my dx. And then I'll leave the 1 over x on the right side. And in order to get rid of the y, I would multiply by y. So I've separated the variables. And then the next step is to integrate both sides. So if I integrate both sides, I'm going to say y squared over 2. I'm not going to worry about the plus c. On the other side, the integral of 1 over x would be natural log of x. I'll go ahead and put my plus c, and that'll represent both of the constants. And I'm going to go ahead and solve for y. So I'm going to multiply by 2. So y squared equals 2 times all of this. And then I'm going to take the square root. So y is plus or minus square root of 2 times this log. And notice the plus c is under the radical, right? Because I took the square root of the whole thing. Now, you know what I did do? I forgot my parentheses right here, so I'll put those there so as not to confuse anyone. Okay, and then they gave me the ordered pair of 1, -4. So if I plug in the ordered pair 1, -4, I'm going to be putting in a -4 for y, and I'm going to put in a 1 for x. Now, in this case, the whole plus or minus business, the fact that the y was negative, that must mean that they were using the negative in front of the square root. So I'm going to put a negative in front of the square root. So it's going to be square root of 2, and then I'll have natural log of 1, and then plus c. So if I simplify, natural log of 1 is 0. So essentially this is gone. And so what I have is that 4 equals the square root of c. And so if I want to solve for c, I'll square both sides. So 16 equals c. So the actual equation that they're looking for is y equals, remember we said they used the negative square root. So square root of 2, and then in parentheses, natural log, absolute value of x, plus 16. And that is the original function. Now, one of the good things about these separation of variable problems, and one of the reasons that we'll spend quite a bit of time going through these, is that it's very likely that these could show up on free response. And when they do, they show up as just one part, like they might just be part B or they might just be part C, but they tend to be worth anywhere from 4 to 6 points. I've never seen them be worth less than 4 points. Usually the points come in this place, in this way. The first point is usually just for separating the variables. So that's the first point. And then the second point, depending on how many they want this whole thing to be worth, it might be that they put 1 point for separating or for integrating the left, a separate point for integrating the right, and then a third point just for remembering to put the plus c right there where it belongs. And then the next point is for just knowing to use the ordered pair. Even if you don't necessarily use it correctly, just knowing to plug that in would be the next point. And then the final point would be for putting it all together and solving for y. So here's a situation where it would be worth up to 6 points. Sometimes, if they don't have 6 points to allot for this, sometimes they'll combine these 2 points and just say, oh, it's just 1 point for integrating both of them correctly. So it just kind of depends how much they have to allot on that particular free response. Okay, so last example. Look at this one, and this would be kind of an example of a multiple choice. It says, write and solve the differential equation. So if we're writing the differential equation, that means we're going to have like dy dx equals, right? We're writing a derivative equation. And then if we're solving, we're doing like we did above, where we're trying to find the original. So it says, the rate of change of r with respect to t. Well, dr dt is inversely proportional. So is inversely proportional means a constant over something. Whereas if they had just said proportional, that would be a constant times something. So if it's inversely proportional to the square root of r, that means it's k over the square root of r. Now, the reason I used k for my constant is because when we integrate and we put our plus c, I don't want you to get that c mixed up with this k constant, okay? So I've written my differential equation. That was this part. And so now let's do the solving part, right? So since I have r's and t's, I'm going to separate. So I'm going to leave the dr on the left, and I'll put the dt on the right. So I need the square root of r to come up over here to the left side with the dr. And since k is a constant, it really doesn't matter which side it goes on, but any constants that are available, I tend to just leave them on the right side, because eventually you're trying to solve for the left side, and it's just easier if you don't have your extra constant business over there. So if I want to finish solving, I'm going to need to integrate both sides, right? So if I integrate r to the 1/2, I'm going to have r to the 3/2 times 2/3. And if I integrate the right side, well, when you integrate a constant, don't you just get the constant times the variable, which in this case is t, and then don't forget your plus c. And here's a situation where they don't give me an ordered pair, so I'm not going to be able to find the plus c, so I'm just going to solve for r. And let's see if we can do this in one step, right? If I solve for r, first I would get rid of this 2/3 that's being multiplied, right? So I would multiply by 3/2. So I'm going to have 3/2 times all of this. And then in order to get rid of the exponent of 3/2, wouldn't we raise it to the reciprocal? So we will raise it to 2/3. So there we have solved for r. Okay, so those two examples should at least kind of get you started and get you ways into the homework worksheet. I think you were given the worksheet, and notice I think side 1 of the worksheet is the first assignment that you're supposed to work on now and have due on Tuesday. And then the second side of that worksheet we will kind of develop more in class on Tuesday, and then that'll be assigned Tuesday and due Thursday. So I realized I wasn't there, and sorry for the wasted day and the issues with the video, but hopefully this helps and gets you started. Please don't just ignore this because you think I wasn't there, because we really don't have time to waste this semester. We've got a lot that we need to get covered. So good luck to you.